To give you a recap, let's talk about the general first-order adjoint state method, which is used to compute the gradient G. Basically, the gradient can be computed in three steps: a forward simulation, an adjoint simulation, and the interaction between these two wave fields. This first equation describes the forward wave field simulation, where the L is the wave propagation operator, U is the wave field, and F is the source. In this study, we use the fractional viscoacoustic wave equation. I'm not going into too many details about this equation and just present it in this abstract form. In this equation, the wave propagator L can be decoupled into three terms. L0, the classic lossless acoustic propagator, L1, the dispersion character, and L2, the dissipation character. This wave equation incorporates the seismic attenuation using L1 and L2, which are featured by the fractional Laplacian operators. For example, in the 2D model, we have a source and a receiver. Using this equation, we can simulate the forward wave field with the propagator L. We have the dispersion captured by L1 and the dissipation captured by L2, which leads to the reduction of the total energy. The second equation describes the adjoint wave field. L star is the adjoint of L, lambda is the adjoint wave field, and D is the observed data. R is a sampling operator that samples the wave field U at the receiver, so its adjoint L star becomes a zero padding operator. In another word, this right-hand side, or the so-called adjoint source, has only non-zero values at the receiver. Last year, we have demonstrated that while the forward wave field U starts from the source and propagates all over the place, the adjoint wave field lambda shrinks to the location of the receiver. And also, since L star equals to L0 plus L1 minus L2, the adjoint wave field preserves the velocity dispersion because of this L1 term, but instead of attenuating, it is compensating or anti-attenuating the amplitude because of this minus L2 term. In practice, we simulate the adjoint wave field in the reverse time mode and with the same simulator as the forward one. Finally, we take the interaction between these two wave fields according to the third equation, and we get the gradient G. So this is the adjoint state method for the gradient computation. Then let's move on to the second order adjoint state method to compute the Hessian vector product H nu for an arbitrary model space vector nu. To illustrate, we consider the case where nu has only one non-zero value that represents a velocity of perturbation right here. Similarly, the computation of the H nu can be formulated by 5 equations. The first two are the same, simulations to get the forward wave field U and the adjoint wave field lambda. The third equation is to simulate the second order forward wave field nu2. The source shown on the right-hand side is the interaction between nu and the forward wave field U. Since nu only has non-zero value at this location, the source only has non-zero value right here as well. So nu2 is the wave field excited by the scatter. Next one is the second order adjoint simulation. Its adjoint source has two terms, so we call them part A and part B, and consider them separately. The source A is R star R mu2, which means the mu2 sample at the location of the receiver and the other points equal to 0. So mu1A shrinks to the receiver just like the lambda. Part B of the adjoint source involves the interaction with nu. So again, it only has non-zero value at the scatterer, so mu1b shrinks to the location of the scatterer. Next, the Hessian vector product H nu is made up of 3 wavefield interactions. We call them H nu1, H nu2, and H nu3 respectively. The first one is the interaction between the U and the mu1. We first consider part A of the mu1. So U propagates from the source, and the mu1A shrinks to the receiver. Hence, the H nu1A has the sensitivity between the source and the receiver. And we record this part of the contribution in here at the bottom. As for part B, still the U starts from the source, and mu1B shrinks to the scatterer. So H nu1B is this fish shape connecting the source and the scatterer. Similarly, we leave the result right here. The second term is the interaction between mu2 and lambda. Mu2 is excited by the scatterer, and lambda has the adjoint source as the receiver. So HNU2 is sensitive to the structure between the scatter and the receiver. Finally, HNU3 is the interaction between U and lambda, and then interacted with nu. Since nu is only non-zero right here, so the loss term HNU3 only has non-zero value as the scatter nu. And we can put together these three terms, or actually four terms. And here we got the Hessian vector product H nu for this nu. Note that this is the velocity part of the product. If we take the interaction in a different way, we'll get the attenuation part, or say the gamma part of H nu in a similar fashion.